our derivation of Ampere's law at this level is going to be pretty elementary. There's a lot more to go into it. This wasn't something that Ampere just like, oh, I came up with. This was actually a brilliant leap. But this is going to come back in, to fold back in, to show us how electricity and magnetism are strongly interrelated. So we'll set this up in any event. Now, suppose that I've got a path where I've got a couple of different cases. And I want to look at and to investigate the idea of the integral over a path of the magnetic field done with dl. Now, in this case, at this path, at each point, the magnetic field is perpendicular to where I am in the center of each dl. So if I look at that, the integral along this line of b dot dl is 0. If I've got some case where I'm moving through space parallel to the magnetic field, then for that path, the integral of b dot dl should just be equal to the magnetic field strength B, if that's constant through space, times L. Now, in a rough construction that's similar to the way we looked at Gauss's law, let's take a particular breakdown. In our brief examination of Gauss's law, we looked at 3 different examples of 3 different forms in which, hey, an equation we set up for Gauss's law gave us a set of consistent results. I'm just going to do that with one case right here and wave my hands a little bit and say, hey, trust me, if you want to go through the math, it will take you through the other side and show you how this works in general. Suppose that I've got a wire with a current going into the board. Okay. For consistency's sake, and the current going into the board. Now, suppose I want to have a circular path. That's supposed to be a circle. Help me out here. Now, for a current going into the board, there are a couple of different ways to find the current from a wire. One way of using the right-hand rule is to say, okay, here's the wire with a current traveling through it. One way to find the direction of the magnetic field is to let your thumb basically hitchhike in the direction of the current, and then the direction of the magnetic field basically follows the curl of your fingers if you're using your right hand. Use the left hand, you get the opposite direction, don't do that. So in this case, for a current going into the board, the magnetic field will be propagating in the clockwise direction. Now, that magnetic field strength for an infinitely long wire will have a field strength equal to mu naught I over 2 pi r, where r is the distance from the wire to where we're interested in. Now suppose I were to take this circular path at radius r and travel in the clockwise direction around this path. So at a given point, I have a differential step, dl, that at every single point is going to be parallel to the magnetic field at that point. So if I were to take the integral around a closed path of B dot dl, what I find here is that, okay, B dot dl is parallel at every point. So B dot dl is simply time equal to B dl integrated around that closed loop. Now the magnetic field is constant because r is constant. So magnetic field around a closed loop of B dot dl is equal to mu naught I over 2 pi r times the integral of dl. Well, the integral around a circular loop is equal to the length of the path, 2 pi r. So my complete equation, my full write-up for Ampere's law, well, for the simplified case I've gotten, the integral of the magnetic field, the dot product of the magnetic field over, dot dl over a closed path is equal to mu naught I enclosed. Now we found that for the most simple case, where I'm just looking at where the only thing in the universe is that straight wire and I'm in the plane parallel to that. But if you look at this in a more complex way, which we're not holding you to right now, because hey, we need something for future years of physics if you come back to us. But we'll find out that Ampere's law written like this is true in every given case. Now it doesn't necessarily have to be even, it doesn't have to be smooth. If I were to draw, say, a set of currents like so, and draw any arbitrary path that were I to take the integral of B dot dl around that path, I would get the result of that integral would be mu naught times the current enclosed. Now, by having some current going into the board and some current coming out of the board, that does have an effect. It has an effect with the sign. if I'm going, basically, it'll be positive if the magnetic field for that individual current is traveling in the same direction as our path around the loop. For example, the magnetic field for I5 is coming out of the board, so the magnetic field lines will be counterclockwise. So the effect for this contribution will be minus mu naught I5. Again, out of the board gives me counterclockwise magnetic fields when we're taking a clockwise loop. So it'll be minus mu naught I3. Heading into the board gives me a clockwise magnetic field that matches up with our clockwise paths. So the contribution of I1 will be plus mu naught I1, and in the same way it'll be plus mu naught I2. I4 is not enclosed. So the contribution due to this current I4 is 0. Does that mean that this current in I4 is not affecting, it's not producing a magnetic field here? Of course it is. But what I'm saying is, since this current is outside this weird path, the effect of the magnetic field here will be the opposite of the effect of the magnetic field at other points, such that the effect of the magnetic, if I just took the integral along this path, b dot dl for I4, the integral that I would get would be 0. Ampere's law, well, we're not going into the details of why, is correct in this write-up, no matter how god-awful your other write-up is.